here we have a curve and what's supposed to be about the same curve here. We're going to look at this curve first. We have an r of t vector that gives rise to a velocity vector, a unit tangent vector, or an r prime vector and a unit tangent vector. What I want to do is look at the unit tangent vectors along this curve at equal time intervals and see what that might have to do with curvature. We're then going to look at unit tangent vectors at equal distance intervals and find that that gives us a better idea of what we really mean by curvature. But let's start with unit vectors at equal time intervals. Now, if we think about what would be the motion along this curve, we go about this far in the first time interval, and we go about this far in the second time interval, and only about this far in the third time interval. So that we have a pretty good speed along the curve here, and we get faster between here and here. Now, we don't know what happens between this instant and this instant, but on the average we're moving faster as we go around here than we are when we go around here, and we're not moving very fast as we go from here to here. However, where is it that this thing curves the most? Does it curve, is the path curvier between here and here, between here and here, or between here and here? It should be pretty clear that as we go from here to here to here, the path is becoming increasingly curvy, so that the distance we travel isn't related very much to how curvy the road is or how curvy the path is. Okay, now I've drawn unit tangent vectors at 4 points, and now I've depicted those vectors all with the same initial point in this picture. So here's T1, our first tangent vector. Here's T2. So as we go from here to here, our direction changes from this direction to this direction. And between here and here, we come back a little bit. So T3 is here, and then T4, we move around this way a little more, so we curve around, so our direction changes as indicated here. Okay, so we have our directions. These unit tangent vectors merely indicate directions. They don't indicate anything about how fast we're moving or how far we go. Now, from T1 to T2, by how much does our vector change? Well, I've drawn part of a circular arc here. We can think of the vectors as being having their initial points here at the center of the circle of which this is an arc, and simply sketching our T1, our T2, our T3, and our T4 vectors just like we have here. But I'm not going to sketch those vectors. I want to sketch the change in those vectors. So between T1 and T2, the vector that indicates our change is going to be this, and we could call that delta T1, 2. And use a red color to indicate that. So between 1 and 2, our delta T1, 2 looks like this. Now between T2 and T3, actually our delta T1, 2 will be a little smaller. I drew it as big as it is on this picture, and my unit tangent vectors are depicted with actually different magnitudes in all three pictures. I don't know that this is going to stay there, but the thing should have a length more like what you see now. Okay, now from T2 to T3, what happens? Well, the change in our vector from T2 to T3 would be just this vector here, and we could call that our delta T2, 3. So between here and here, we have a delta T2, 3 that might look like this. And then between our third and fourth point, if I can fish out a marker of a different color, we would have a delta t 3, 4. And that looks to be actually a little longer than the delta t 2, 3 down in this direction. So corresponding to the interval between t3 and t4, we have delta t 3, 4. Now delta t 1, 2 is clearly the largest of the three vectors, and I made that too big as well. That should be about the same length as this one. Not sure I can work into this curve and make that happen. Just understand this should be a little shorter than what I drew. But now the point is that this is how much our unit tangent vector changed between here and here. This is how much it changed between here and here. And this, if it's made a little shorter, is how much we change between here and here. This one is probably shorter than this one, but it occurred over a much shorter interval of our path. And that kind of indicates that our path is curvier here because we got almost as big a delta t over a much shorter part of the path. Another way to look at it is we were moving a lot slower here and we still got a pretty good change in our delta t. So looking at unit tangent vectors at equal time intervals doesn't really show us how quickly or how curvy our path is. It just shows us how much we changed at whatever speed we happen to be moving on that interval. So this picture is in some way related to how curvy the road is or how curvy the path is, but it doesn't really give us something that we would want to call the curvature. Now, if we look at the unit tangent vector at equal time intervals, at equal distance intervals, then we're going to get something that plausibly indicates curvature. So we have more or less equal intervals of distance here. Now, of course, distance is measured along the curve and so forth. It's not measured as a straight line between points. But here's the picture that we get for equal distance intervals. Here are the vectors that we get, t1, t2, t3, t4. And here we have a picture similar to this one where we're going to be able to trace out the differences in these vectors as they appear on different distance intervals.